Well, thank you very much. Thank you for having me here. This is going to be a bit of storytelling because it's the end of a very long day. I'm sure a lot of you are jet lagged or arrived very late, and therefore, yeah, let's not keep it too technical. I hope it's going to be, you see, this thing makes me a bit nervous. I normally don't wear these, and you can see they're just not very outfit friendly. Also now I've seen you all splash about with those. I think wearing black was also a really bad idea. So, well, let's see how it goes then, huh? So we are literally going to discuss this because if you're just picturing a stable model category in your head, whatever your favorite one is, let's just list some examples. I'm sure your favorite one, well, most of your favorite ones will be on there. I don't know, people have weird taste, right? So think maybe of your favorite kind of spectra, or your favorite category of modules over some ring spectrum. Or, well, if you have a favorite homology theory, then you can think of E-local spectra, maybe left local or right local or whatever you like, or chain complexes in your favorite abelian category. There are quite a few. Now, let's see. Yeah, I mean, there's two buttons here, one up, one down for each board. How hard can it be? And yet. So then, of course, when you look at these and somebody may ask which of these is algebraic and which of them isn't, people might have some kind of intuition what the answer should be. That probably yes, and those depending on what R or what E is, that one certainly not. But yeah, when you just read around and look at things that are floating around, algebraic isn't really particularly rigorously defined. Different people, different sources seem to mean different things by them. So our goal was just to look at some reasonable ones and see how they are related, how they are implying each other, and what we can maybe find out about our favorite stable model categories. So the kind of one version of algebraic that I will actually use as algebraic that we can probably all nod our head to is that a stable model category C is algebraic if it is a chain Z model category. So chain Z model category, analog of simplicial model category, so something that is tensored, co-tensored, and enriched in a homotopically meaningful way over chain complexes. And I'm sure everybody would say, yeah, I mean, if it's that, it certainly deserves to be called algebraic. But unbounded, yeah. But what does that mean in practice? So by Morita theory of Schwede and Shipley, we know that every stable model category under some mild niceness assumptions, if it's not even that, then we don't want it, is Quillen equivalent to a category of module over some ring spectrum. And not just any ring spectrum. Actually, that ring spectrum is going to be an endomorphism ring spectrum where, let's just keep it simple and say our model category has a single compact generator. If it doesn't, one can generalize all this. And so just looking at that, we will see that C is algebraic if and only if, well, algebraic would mean that, of course, the enrichment in chain complexes would tell you something about the structure of these things, and in particular, it would tell you that this ring spectrum would have to be an Eilenberg-MacLane spectrum of an endomorphism DGA, so, yeah, that's algebraic. However, I mean, I can now, of course, say, okay, that's the end of the talk, let's go and have dinner. But it's not going to be until 1930, so might as well. How hard can it be? Might as well see if we can maybe refine this a little bit. So any stable model category comes with further structure, of course, a lot of further structure, but the one that I'm particularly interested in is the following. So for any stable model category C, you have a closed module structure over the stable homotopy category, like so. It's just like in any model category has things like homotopy mapping spaces, or rather homotopy mapping simplicial sets. If your model category is stable, for example, every stable model category has homotopy mapping spectra in a nice way. But this doesn't necessarily need to hold without putting the up to homotopy in there, but up to homotopy, at least we can look at tensors up to homotopy and mapping spectra up to homotopy and can ask ourselves, yeah, what does that have to do with being algebraic? Well, if C is algebraic, then the following happens. Namely, this module structure here will factor over the derived category of integers. And so in particular, it means if you have this dz action, it means that in particular your homotopy mapping spectra aren't just any old spectra, but they're Eilenberg-MacLane spectra or HZ modules if you want. It's not an if and only if, because in order to reassemble this from just these ones object-wise being Eilenberg-MacLane spectra, you would have to show all kinds of coherence maps aren't just maps of spectra, but maps of Eilenberg-MacLane spectra, and but it doesn't really matter at the moment. But what matters just now, this of course seems to be therefore a little weaker in the sense that algebraic, and here we go again. Where is the implies that you have this dz action. Does it go the other way? Probably not. I mean, you can probably already just tell from the fact that I'm asking that question, but let's just put a question mark here for the moment. It's a genuine question mark because for some time we were...
Sorry. That's already the definition of algebra, or I'm mistaken something, like the fact that you have being tensor over...
Yeah, and of course, if you then say, okay, now I want all this up to homotopy, then you get that.
Okay.
So that one is easy. Okay. But what about the other direction? So well, it's actually not true. So why did I even bother with this? So it's a really nice counterexample. So of course, as Leonard pointed out, all the topics of this conference, let's have some K-theory. So we can, for example, take hz as a KU module by just killing the bot element. We can do that. And then we can look at the following lovely spectrum E, which is the endomorphisms of hz as a KU module, which indeed is the endomorphism ring spectrum of hz in the category of, I didn't leave enough space, did I? You take KU modules and you write Bowles field localized at hz. Doesn't really matter. All that I'm trying to say is that this spectrum indeed is of the form end of x in the above setting. And well, this thing, it's a ring spectrum, so it's an S algebra. And it is also an hz module. But it is not an hz algebra. So this module category, it has dz action, but it's not algebraic, because there is this teeny tiny subtlety that you might think that being a ring spectrum that's an hz module is also an hz algebra, but in fact it isn't. We try to prove this thing. That must certainly be one of the special features of Allenberg-MacLane spectrum. We tried to prove it. It was 2020 and intuition was off, and we tried to prove it, and then we thought, we are three reasonably sensible people and we haven't managed to prove it, so maybe it's just not true. And indeed it wasn't, because there you go. Well, it's not exactly the same, right? Well, if it was, then you can form the following thing. You can now look at the endomorphisms of hz in E modules. And I now put that in completely the wrong place. So I wanted a square like that, with this one at the bottom right. If it was, then of course you would have a ring map from here to here, and therefore also, because the sphere is initial with stuff, a map from here to here. But what people, John Greenlees being one of them, but not the only one, know is that this map also factors over Ku, and it doesn't just factor over Ku. That one is a weak equivalence, and if you were allowed to add this and looked at what that diagram meant, it would be that the unit map of Ku would factor over hz, which it doesn't. So that's a big fat no. So therefore, there are actual counterexamples that is genuinely stronger than this, which isn't really a surprise if you look at the definition, but I mean, we have to we have to make sure of it. So, but we could maybe weaken this notion a little further. Because, I mean, if you have this, oh God, now I can't see what it is anymore. If you look at this closed module structure there, I'm still writing, aren't I? Then this top row of the triangle tells you that in C, the morphism groups come with an action of the stable homotopy group of spheres, because you could just take any morphism and smash it with something, an endomorphism of spheres. And that's really the reason that topology is better than algebra, because we have a sphere. And the sphere is much more fun than the integers. So, so what if we weakened this action of the sphere, and so how trivial can we make this action of the sphere, and what does that have to do with being algebraic? Because being algebraic certainly means that all of the nice features of the sphere are dead. So that leads us to the following. We say that the homotopy category of C has trivial action of the stable homotopy category if the sphere acts trivially on morphisms. So we could just reduce that to saying that X smash alpha is trivial for X in C, and alpha in positive degrees of the stable homotopy groups of spheres, because obviously I can't just ask for integer multiples to be trivial. And it is in fact enough to ask this for X being a compact generator of C. It's not as easy as it may sound, because we do not have a 5 lemma or anything for zero maps. But you can reduce this to compact generators if you want. So let me write this, because I will actually use it. So now I have something else to put on the board, namely trivial action. So many boards. Yeah, and then of course the natural question to ask, how is this related to it? And I already gave it away. This one will imply this one. Well, why is that? So, if I take an alpha in pi k as node, and I look at X smash alpha, that will live in here. And of course, under the adjunction over there, this will just correspond to a map from the sphere into the mapping spectrum of those two. Is that what I call it? Yeah. But of course, I mean, I left this gap here for a reason, but it doesn't just correspond to any map. It corresponds to the map. Well, first you do alpha from Sk to S node, and then you do the unit map into this ring. And so if you have a dz action on C, and all of these are Eilenberg-MacLane spectra, and K is positive, then of course that is trivial. If we have this action here. But then, obviously, what about the other way? Do we really discover and recover an entire dz action if all the elements of the stable homotopy groups of spheres act trivially? Well, no, this is another new thing. Because, well, now, more K-theory. So if we take C to be modules over nth Morava K-theory, then, well, Kn is a compact generator of that. The endomorphisms of this compact generator in Kn modules is just Kn again. And we also know that Kn is not an Eilenberg-MacLane spectrum. So clearly we don't have any dz action on this, let alone being algebraic. So now what will happen if we smash Kn with something from the homotopy groups of spheres? You've had enough coffee to remember that. So if we take some alpha in positive degree, and then, I mean, what will this be? This alpha will be nilpotent, because they all are. And what happens if we smash something nilpotent with Kn? It dies. So yeah, and I mean, there you have it. Here is an example of something that has trivial action. But doesn't have any dz action. And yeah, I will, this is one of the things I will certainly never ever forget, even once I don't recognize family members anymore. Because that is something that came up in the final version of my PhD thesis, and I tried to prove that something was nilpotent by hand, and I just couldn't work it out, and I couldn't work it out, and I asked Hans-Werner Henn whether that was nilpotent or not, and he also couldn't really work it out. And then he got my thesis to read as an examiner and said, well, it's just trivial once you apply K1. And yeah, so would have saved me 2 months of agony if I'd said that the first time I asked. But but I've long forgiven that. So and of course, the same argument also works with little Kn modules, so connective K-theory, or MU, or anything that detects nilpotency. So that's a relatively simple way to get a free example. But of course, as wonderful as the sphere and its endomorphisms may be, they are also quite difficult to handle from a computational point of view, aren't they? So yeah, it's not the sort of ring where you easily can write down some generators and hope for the best, but we can still do something a bit like that. So the elements of the stable homotopy group of spheres of Adams filtration 1, they generate this whole ring in the sense of So everything in this ring is a long matrix-valued total bracket of things in lower Adams filtration. So, yeah, because I'd rather wouldn't really want to spell out exactly how. You can go and read the paper. Good luck. So, well, let us just jump straight into the next definition. We can say that the homotopy category of C has essentially trivial action. If all these elements in Adams filtration 1 act trivially, so if all eta, nu, sigma, and the alpha ones act trivially, in the sense that if you smash them with x, it's 0. So, new thing. I mean, while this paper hasn't reached its final published version yet, if you can think of a better name than essentially trivial, I'd be glad to know. Because, you know, just remember when you were all young and fresh undergraduates and learning about what a vector space is and things like that, and you were dreaming of the day where one day you can do research and you can name things. And then you get to that point, and at least I realize I just can never really come up with anything good. And oh, that's see, some people just have a natural. None of my co-authors do. Sorry, it's recorded. I stand by it. Yeah, it's especially a problem when you have children and you realize you're bad at naming things. That's, so they have better names than that, honestly. But in this case, I can honestly say I just don't know if those two things are equivalent because they look like they should be. But, well, you can't really tell. So if you take an x smash alpha, then, because smashing with something is still reasonably nice, and, well, if your original alpha was in a long matrix value total bracket, let's just write something here, then x smash alpha is going to be in a long matrix value total bracket with entries x smash whatever was in there before. And then you can say, oh, okay, so I'm going to add my induction here, and therefore all of these vanish, or at least enough of those vanished, and so I have a long matrix value total bracket with lots of zeros in it. And yeah, I mean, that will actually contain 0, that's true. But I mean, that is a set, and just because these two things are in the same set doesn't mean that they're equal, sadly. But then, you know, you think you've been through things and you can maybe handle some calculations, and indeterminacy for threefold total brackets isn't so bad, so maybe one can also work out how that works well. Once I found out that in the stable homotopy category, so total brackets on the homotopy groups of spheres, the total bracket of 2002 has indeterminacy eta squared, I thought there's just no hope. So unfortunately, one cannot just write down a simple proof that these two are equivalent, and even when you read the paper where this induction thing is described, I still couldn't do it. But one could say at least a little more about this, and that now seems a bit like a niche thing, but for examples it actually does come up. So if you take this action of the stable homotopy category on Ho of C, and if it factors over the k-local stable homotopy category, then these two things are actually equivalent. Well, why is that? Well, I mean, it's not like this is any more calculable. Well, it's not like the k-local homotopy groups or spheres are any less complicated. But you could, let's just say we're working too locally for simplicity's sake. If you can show that these ones act trivially by hand, or rather we've assumed it here, then you can show that the first 8 degrees of the homotopy groups or spheres act trivially, and then you can wedge the sphere action between some k-local Moore spectrum action, and that's 8 periodic, and then you can retrieve everything from that. So if you can show for some reason, because you know some stuff about what this is, that it factors over the k-local stable homotopy category, then it is really enough to just check it on the Hopf elements. And now here we go. You can't do 2 of them simultaneously. No. Well, so now you have plenty of time to think, and now you have more time to think because I have to clean. Yes, please.
So, are you using Joe Cohn's paper?
Yeah.
Yeah. But I mean, actually, what he says is you have to include, well, locally, you have to include 2 as well. I mean,
Yeah. So you have to make sure that you don't have like 2 2s right next to each other, but that wouldn't happen. Sure.
So if you took the sphere spectrum and modded out by these elements in the world of infinity ring spectra, is that thing like known, not Bezier, like is that related to people that?
I've never thought about it like that, but
I mean, thinking of
yeah.
the question of whether you have the reverse implication, like if that thing is non-trivial, then that should give you a counterexample to that implication. Modules over that quotient who have the property that
Portion of what?
of the sphere by all of these elements you listed.
What is the sphere once you've divided all of those out, though? Maybe it's just not that thrilling anymore.
Sort of like, I don't know, I don't know, some.
Yeah, I've never thought about what that could be, but I'm worried that you just turned the sphere into the integer doing that. So.
It seemed like that would violate some form of Mahold's uncertainty principle.
Ooh.
But
Well, now it sounds like it's getting interesting.
no, it's probably related to the Coda brackets.
But do you want to do E1 portion or infinity? Why?
I don't know. Maybe one is better to do the module.
Infinity portion could
I mean, if you do what Basil says and you kill Ada and U, you don't kill sigma, so you have to kill at least those three. But that's still not clear that you get nothing.
Well,
Anyway, epsilon,
yeah.
so
Hmm?
What? You write the element epsilon in the eighth stem as a curly bracket without using 2.
Epsilon. Yeah. Well, you can use 2, it's fine. Yeah, you just have to make sure that in your total bracket you don't have 2 2s right next to each other. So I'm concentrating more on that than I am on the sphere right now. Because I mean, it's not even that I haven't written on the blackboard in ages. For teaching, we don't even write on boards anymore. I don't miss the chalk dust and all that, but I mean, still got it. Ha. But what about these k-local examples? Of course, you could just go and take a ring spectrum, and now let's do all primes rather than let's pretend we're all p-local for an odd prime, so we only have to think about alpha 1 rather than 4 of them. And of course, we could just look at r smash alpha 1, which would go from here to here, or 2p minus 3. And well, if your R was a spectrum with homotopy groups concentrated in certain degrees, maybe even degrees or whatever, then that would be trivial by degree reasons. But then I can only really use the criterion that these two things are equivalent if I factor over the k-local stable homotopy category if my mapping space is in here and therefore the R itself are k-local. So for example, I could do so for example, for my examples, I would like a ring spectrum R with the homotopy groups concentrated in nice degrees. And I would like the mapping spectra to still be k-local. So for example, I can take C to be E1 modules or KUP modules or, well, KOP as well. And then I do have examples of things which are essentially trivial and therefore also trivial because of my k-local condition. But, I mean, now I need to ask Irakli, if he hasn't fallen asleep yet, what do these have in common?
Well, I mean, their homotopy categories are equivalent to the homotopy category Petit, homotopy.
There we are.
So they are algebraic.
So I should come in with a microphone, but so what these ones are, what these ones have in common is that they all fall into this Franke equivalence type machinery that Irakli and co-authors have worked out so beautifully, namely that if R and pi star of R are sufficiently nice, then you can get that's the homotopy category of R modules is triangulated equivalent to the derived category of R star modules. But of course, these two are not Quillen equivalent. So that's just a triangulated equivalence that is not coming from an underlying Quillen functor.
This is joined with Piotr, and I only managed this.
Is that a test whether I can write a surname? Starowski? No? Magdalena, what do you say? Starowski, okay. Well, they put their 115-page paper on the archive the same day we put that one out. You can read them in parallel, for sure. Or if you want to take a break from this, then maybe. So, which brings us to the next classification, which doesn't really fit into this picture at all. So, of course, you could ask all these four different things from your stable model category, and they still have some element of homotopy in there. But what you could also ask for is for your model category to be triangulated algebraic, which means that just up to triangulated equivalence, it looks like something algebraic. So something is triangulated algebraic if it is equivalent, just triangulated equivalent to something else, with this being an algebraic model category in the strictest sense we've had so far. So clearly, that will imply that. And also because of the kind of original Franke theorem, that one absolutely does not imply this, because, well, there are these examples. There's one on the board right there. That one is algebraic, therefore this one is triangulated algebraic, but it is not algebraic itself. So another triangulated algebraic example is, well, the classical Franke equivalence. Well, let's just call it. Let's just let it go from here to here. Because of Franke's functor, k-local spectra are triangulated algebraic, but clearly there are absolutely none of these things here. They do not have essentially trivial action, because if you smash with the relevant elements, it doesn't just vanish, and they certainly don't satisfy any of the other things. So triangulated algebraic doesn't really retain any homotopy information. However, well, not really however, but that is really why I found this question interesting to begin with, is so one can show, or rather I have shown ages ago, that any such exotic model for k-local spectra has essentially trivial action, because once you get into the uniqueness proof for p equals 2 and you're trying to see what goes wrong for odd primes, at some point you have to ask yourself, where does alpha 1 go? And it's either 0. I didn't move. It's either 0 or it's not. And if it's not, then you recover this. and if it's 0, you get an exotic model. But yeah, what we do not know yet, and what I would really like to find out, first of all, we do not know if Franke's exotic model is unique in any way. Is it really the only such thing that modules this triangulated category, or are there others? Any of the others that might be out there would have essentially trivial action, but would they also be algebraic in the top sense? So really the main motivation behind starting this was because I really wanted to find out if any exotic model would be algebraic or not. And of course, I'm nowhere near closer to answering that question, but at least I now have a better grasp of what the difference will be. So that is one of the things that I would like to find out. And other questions that remain apart from that. You see here that triangulated algebraic is really quite lonely in this whole list of implications. If at some point you might open our paper and see, if I ever did a slide talk, then I could have put that on the slide. There's a very lovely diagram with how all these things imply each other. And it would be just very nice if there is really anything meaningful that would imply triangulated algebraic, because at this moment we really only know that these things exist because they're all special cases of the Franke machinery.
What about if you have if you look at the associated stable derivatives, like that sits certainly between algebraic and having a derived category Z action, right?
Does it?
So if you take your stable model category and look at the associated stable derivator, then it has, like every stable derivator, canonical action of the one associated to stable homotopy. But then you could have a new definition of algebraic as saying it factors through the stable derivator of abelian groups, chain complexes. But it seems to be in between those three in the corner, right?
Well, I'm very, very happy that you say something like that, because really my next question would be if there's anything that you could still fit between the ones that exist, or if there's any kind of interpolation theory where you can say, okay, I have to overcome these obstructions to get, let's say, from here to here, or from here to here, and if I maybe can't get all the way from here to here, I could at least say maybe how far I can go up, or rather how close I am to having a DZ action or to something algebraic. So maybe I have to learn about derivators again.
I think actually I like also between this algebraic and triangulated algebraic, and maybe Piotr will correct me, but like there are these higher truncations of the C, right, sitting in between as well, and you could ask up to what level it's algebraic, and it could be related to some of these homotopy groups, because we see some homotopy groups up to some level of this.
Yeah, I do try and read that, yes. Yeah, one would hope so. It certainly seems to be for these particular examples that you can say something about it. I wasn't sure how you could generalize that to just...
obviously there are some stuff in the middle.
Yeah. So it would be great to have some idea of obstruction theories. And also, maybe I'm not going to write this down, also around the same time, there was this paper of Leonard and co-authors about finite localizations, like VN localizations. Let's see how they fit into that picture. That's something I'd like to see. And also, at some point, I'd like to learn about motivic homotopy and see how that fits into that picture. But yeah, it's been a full last couple of years, and a lot of things got left behind, but I'm hoping that I can pick them up again soon. And if any of you nice people ask or discuss, then hopefully maybe some of these things get moved forward. And until then, that's how it remains. Thank you very much. I don't know.
I mean, he has some discussion about the ensemble model, and I thought there was some sense in that was very close to being one.
Well, clearly you know that better than me, so maybe we should talk.
John, do you know that?
It's a position where there's only two layers in the
It's in Ragagnon's localization. Maybe there's some reason why it's not like. Or it may be just a simple consequence of that. So.
Well, let's have a look.
More questions? Yeah, Stefan?
I think some people, like Stefan Schwede and also Bernhard Keller, use as a definition of an algebraic triangulated category that the category is triangulated equivalent to the stable category of a Frobenius category.
Yeah.
Is this equivalent to yours or stronger?
We did have a look at how this fitted in. It didn't seem to have a particular application to the examples that we were considering because there were just too many things that were not known in that other setting. But yeah, they aren't completely unrelated because there's still quite a lot of open questions about some of the things that Stefan conjectured.
I mean, do they show in one of those papers that like this is equivalent to asking that it's H0 of a pre-triangulated TG category? I mean, so which you are in your definition, right?
It seems like one implication could hold, but the other one
It's not characterized as always the definition, try to show you. Let's see.
More questions?
So this nice example you computed for us for the first implication is not reversible. Is there any can this be more general somehow? Like, or is this? Seems like anything very specific to
That seems to be quite a specific computational thing that this right-hand vertical map is some kind of completion map.
You don't have any other examples of this implication?
Well, not at the moment. I did look at some of the sources, but they seem to be very much specified to that one. Because there's some spectral sequences and...
Would there exist a special example, not universal, but some kind of special property that you show the existence of without knowing what it is?
Well, I mean, that one we know what it is, and it's nice.
It's very nice. I like
Yeah.
it. You know, theoretically, could be some.
I would have to look at it more to really answer what would gain by extracting the assumptions from that. But I think it is mostly very computational, so.
One attacking the abstraction.
Yeah, maybe. But I don't really see how you would get an obstruction to go, like how close you will get to being an HZ algebra. I don't know if that's really the right context for that.